Good afternoon, guys. This is Professor David J. De Los Reyes. I am now on topic lesson number 4 on my course Differential Equation. Okay, let's proceed for this afternoon. My topic on my channel, okay, under the topic Differential Equation, I am now on DE04, Differential Equation lesson number 4. On my channel, the topic Differential Equation, the subtopic is first order differential equation. And under the main topic, variable separable, number 3. Number 3 meaning I am now giving you a third example on the variable separable first order differential equation. Okay, I will try to rectify. Evaluate the differential equation dy dx equal to 1 over x squared minus 1. X is equal to 2 when y is equal to 0. Well, we are given this differential equation. For the meantime, it contains derivative. Okay? But if we try to bring out the solution, we will multiply all terms by dx. This cancels. Left hand side, what remains will be dy. Right hand side, it will be dx over x squared minus 1. So after the multiplication of dx, we already separate the variables. We have done already the title of the topic, variable separable. We separate already the variables. Why? The variable on the left hand side, what remains is just y, and on the right hand side, it will just be simply x. So actually, we separated already the variables. So the next thing we do is to bring out the integration process. Taking the integral of both sides, the integral of dy equal to the integral of dx over x squared minus 1. If you try to observe the right hand side, it's a quadratic equation, right? If the right hand side is just simply x, we could use the natural logarithm, okay? But since the power of x on the denominator is 2, if you try to take the differential of that one, it should have an x dx. And if you try to observe the numerator, it is simply dx. So it does not fall under the so-called natural logarithm for the meantime. So if you try to recall all the different integration process under integral calculus, I think the proper solution, one of the proper solutions should be using trigonometric substitution. Okay? We will let x squared equal to secant square of theta. That is our trigonometric substitution. Okay? Taking the square root of both sides, x now will be secant of theta. Perfect square, x equal to secant of theta. Computing for dx. dx will be, the differential of secant is actually secant tangent times differential of theta. I mark this in a red rectangle because later on I will be getting this value here on the substitution on the problem. Let's try to compute for the value of x squared minus 1 as a function of theta. X squared minus 1 equal to secant square of theta minus 1. But we know that we got a, what you call this, we got an identity 1 plus tangent square of theta equal to secant square of theta. We got this identity here. So we will replace the value secant square of theta minus 1. We transpose this one on the right. Then we try to rearrange. So what will come out will be tangent square of theta. Right? So we could replace now secant square of theta minus 1 by the value of tangent square of theta. Okay, going back to the integral of the right hand side. The integral of dx over x squared minus 1, it is this. Equal to the integral of, what is dx? dx is just this. Okay? Secant tangent differential theta all over x squared minus 1. But x squared minus 1 is actually the square of tangent square of theta. Tangent theta, tangent theta. So 1 tangent of theta cancels. So what will remain will be the integral of secant over tangent times differential theta. Secant theta is actually 1 over cosine. And 1 over tangent is cotangent. And cotangent is actually cosine over sine. So again, this cosine of theta cancels. What will remain will be 1 over sine of theta. But 1 over sine of theta is cosecant of theta, differential theta. For the meantime, this is not yet here. Okay? It is just simply cosecant theta, differential theta. Then if we try to multiply the right hand side by the quotient, cosecant plus cotangent, cosecant plus cotangent, this is actually 1. Okay? But we could insert it. There is no violation algebraically. So what will come out will be cosecant will be cosecant squared, cosecant cotangent will be cosecant cotangent. Bottom portion, it will be cosecant plus cotangent, close bracket, differential theta. I think this now falls under the natural logarithm. Okay? It will fall under the integral of du over u, in which it will be natural logarithm of u. Okay, let's try to verify the value of u. The value of u is the one underneath. The value of u is cosecant plus cotangent, taking the differential. Let's verify the differential. Differential of u will be, the differential of cosecant is a negative cosecant cotangent, and the differential of cotangent is a negative cosecant square of that angle, close quantity differential theta. If you take the differential of a cosecant, it should have a negative sign. For cotangent, it should have also a negative sign. We will factor out the negative sign. So this is du will be negative open quantity, cosecant cotangent, cosecant square, close quantity differential theta. If you try to observe the value of du, then compare it, the one on the numerator, it's almost the same except for the negative sign. So if we try to insert the negative sign inside, and we counter that one by placing a negative one outside the integral sign, it now falls under the natural logarithm. So the integral of dx, which is over x squared minus 1, will now be equal to, this is preceded by negative sign. Negative, this one now falls under the natural logarithm. Natural logarithm of the quantity cosecant plus cotangent plus k. The constant of integration. We are now given the general solution. Okay, that's a part of the solution. Okay, let's try to bring out the equivalent of cosecant and cotangent in terms of x. From the relation or from the substitution, secant of theta is actually x over 1. It is for this. It is this. Okay. Secant theta is actually equal to x, or simply x over 1. Okay. Secant is actually the reciprocal of cosine, so it will be x over 1. So meaning we are given a right triangle in which the hypotenuse is x and the adjacent side is 1. So the opposite side will be the square of the hypotenuse minus square of the adjacent side, and take the square root. So in here, it is where we will get the relation of cosecant and cotangent in terms of x. Cosecant of this angle is hypotenuse over opposite. So it will be x all over the square root of x squared minus 1. Okay. Cotangent of this angle will be adjacent over opposite. So it will be 1 over this square root. It is 1 over the square root of x squared minus 1. Let's take the sum of cosecant and cotangent. It will be x over this plus 1 or plus 1 over this square. Then we can combine, same denominator, it will be x plus 1 all over the same denominator. Meaning the sum of cosecant and cotangent is actually this ratio here in terms of x. Okay? Therefore, the integral of dx over x squared minus 1 equal to the natural logarithm preceded by negative sign. Okay? The sum of the cosecant and cotangent is actually x plus 1 over x squared minus 1. Square root is actually raised to the 1/2 plus k. And if we try to simplify this one, okay, I didn't show you the simplification, we lack space. What will come out for y now? This one is actually equal to y. It is the left hand side, it is. Right? Therefore, y now equal to 1/2 the natural logarithm of the quantity x minus 1 over x plus 1 plus k. This is actually the general solution. Okay, general solution in terms of x. Okay, so let's try to compute for the value of k. The given initial condition is that x is equal to 2 when y is equal to 0. 0 will be equal to 1/2 the natural logarithm. 2 minus 1 will be 1 and 2 plus 1 will be 3 plus k. And k now will be equal to 1/2 the natural logarithm of 3. Okay, so the particular solution, it will just be simply y. We will follow this 1/2 the natural logarithm of the quantity x minus 1 over x plus 1 plus 1/2 the natural logarithm of 3. Particular solution. Okay, and this is our final answer. I didn't show you the complete simplification of this, but try to take your rough draft. For y, it will be this as a general solution. K, it will be 1/2 the natural logarithm of 3. Final answer for the particular solution, 1/2 natural logarithm of x minus 1 over x plus 1 plus quantity plus 1/2 the natural logarithm of 3. Particular solution. That is variable separable. Okay, example number 2. Okay, good afternoon, Los Angeles.